It's Nerf or nothing. Nerf, or non-expanding recreational foam, was created by the Parker Bros. The Parker Brothers have also created games such as Scrabble and Monopoly. You win some, you lose some. The Nerf guns are now owned by Hasbro, but Hasbro prefers to call them Nerf blasters to avoid controversy with gun control and gun violence. Nowadays, Nerf is commonly known, but just like the band Bon Jovi, they came out in the 1980s. Nerf guns are a great example of physics. Physics.
Dude, what the heck?
Physics. Although a Nerf gun is designed to look like a real gun, it's actually quite simple. A spring is inside here and gets compressed to store energy. When the spring inside the barrel is compressed, it's storing spring potential energy. This stored energy will later be converted into kinetic energy to get the dart to fly through the air. By pulling the top of the gun back, the spring is compressed inside the barrel. This allows for a mini locking mechanism to hold the spring in place. Not really sure what mechanism means, but man, it sounds scientific. When you pull the trigger, the locking mechanism that's holding back the spring releases, allowing the spring to return to its equilibrium point. This is how the spring potential energy turns into kinetic energy. So we got spring potential energy and kinetic energy, but how much energy do we have? Well, to find that, we have to work backwards. So let's jump forward to the end. For the Nerf gun that I used, the bullet was shot 5.67 meters when shot from a height of 0.73 meters off the ground. Since the gun was at rest when it was shot, the vertical velocity initially is 0. We also know that due to gravity, the acceleration of the dart in the vertical direction is 9.8 meters per second squared. So let's see, we have the change in height, the initial velocity, and the acceleration. Since we have three components of kinematics, we can use a kinematics equation to fill out the rest. For the horizontal, we only have the distance traveled, and if we're trying to figure out the velocity, we're going to need the time. The time in the air vertically is the same as the time horizontally, so let's use kinematics to try and find our time. Using the equation delta y equals VIT plus 1/2 AT squared, we can plug in our known values to simplify. Delta y is our change in height, VI is our initial velocity, and our A is just our acceleration. Now that we have our delta x and our t, we can figure out V. A little bit of algebra helps us see that the bullet shoots out at 14.69 meters per second, or 32.86 miles per hour. As you can see, that's really fast. But don't worry, I'll go over later how a Nerf gun is completely safe to use, as long as you don't get shot in the eye. But for now, let's get back to energy. Kinetic energy is found by multiplying 1/2 by the mass of the object times the velocity of it squared. These foam darts are very light, weighing in at about 0.0014 kilograms. And using our velocity that we found before, we can find that our total kinetic energy is 0.151 joules. This means that our spring potential energy from the beginning of the problem is also this amount, since energy is conserved. So that answers that question about how much energy there's in the spring, but what is the spring constant of the spring inside of a Nerf gun? Well, we can find that using the spring potential energy equation. Spring potential energy is measured by 1/2 times the spring constant times the distance from equilibrium squared. This just simplifies into 1/2 kx squared. By measuring the barrel of this gun, I was able to find that the spring is compressed a total of 0.045 meters. Now time for some more algebra. Algebra lets us know that our spring constant in the Nerf gun is 149.14 newtons over meters. This just means that 149.14 newtons is needed to stretch the spring to 1 meter. So it makes sense that this number is really big since the spring is so small and needs to be stretched a whole meter. Don't get confused, because spring constant is a lowercase k, while kinetic energy is a capital K.
Didn't you say earlier that the bullet shoots at 14.69 meters per second? Isn't that dangerous?
No, you uneducated kid from Iowa. What are you, 12?
Actually, I'm 11.
Like I said earlier, a Nerf gun is completely safe. If not being shot into someone's eye, of course. It's all about momentum. When a Nerf dart hits and sticks to a Velcro vest, it is a completely inelastic collision. That's just fancy talk for saying the two stick together. Like any collision, the momentum is conserved. The momentum of an object is just the mass times velocity. The momentum of the dart before it hits the person in the vest is very small, only 0.0205 kilogram meters per second. This is because of its small mass. Therefore, when the dart hits the vest on an average sized person, around 70 kilograms, the momentum must also be 0.0205 kilogram meters per second. Since their combined masses are 70.0014 kilograms, the velocity is going to be very small. It turns out that this velocity is 0.0003 meters per second. This means that when someone gets hit with the dart when they're wearing the vest, they're actually shot back 0.0003 meters per second, which is not noticeable, so doesn't hurt. Momentum. So, let's review. Nerf guns are a great example of physics. They show the conservation of energy, projectile motion, and collisions. Also, by looking at the momentum of the dart through the air, we can find that playing with Nerf guns is completely safe. But instead of me just telling you all the physics behind Nerf guns, here's a real life example.
Alright, just go up to the contact on the bench and say the code. He should have what we're looking for. Ultimate Frisbee is the best sport in the world.
You got the money?
You got the stuff? You're a good man.
Hey! This isn't all of it!
That's because I already know some physics. Allow me to demonstrate. Spring potential. Kinetic.
Oh no! The collision!
Don't worry, the momentum in that dart is so small it won't even be dangerous.
Unless they hit you in the eye.